study atomic structure, right? Okay, so you are all already familiar with the periodic table of elements, okay? And then of course you are familiar with atoms, okay? So sometimes people get confused, what's the difference between an atom and an element? Well, okay, they're basically the same thing, okay? So if you look at an element, it's just made up of one atom type, okay? So if I have this piece of lead here, okay? Okay, so it's just got lead atoms in it. Of course, in this piece of lead, okay, there's trillions and trillions and trillions of atoms, because atoms are really small. Okay? An element is just defined as just that one atom type. Okay? To make things simple, okay, with periodic table and with elements, use symbols. Okay, so for lead, which I just showed you, lead, okay, its symbol is Pb. Okay, a lot of these things are Latin in derivation, so they use Latin symbols. But something like carbon, that's much simpler for us, just C, oxygen is O, hydrogen H, and so forth. Okay, okay, so atom on the other hand is, it's like an element, okay, it's the smallest part of the element, which keeps those properties. Okay, I just put the smallest part of the element, but it keeps those properties. So if I was able to take this lead and cut it in half, cut it in half, cut it in half, keep doing that forever almost. Okay, you get down to one atom, okay, and once you split that apart, you'd be splitting the atom apart, which you can do, but not under normal situations. All right, so models. How do we picture atoms? They're so small you can't see them with your naked eye. Okay, so scientists come up with models. Okay, probably the most common one we use is this Bohr model. Okay, which has a nucleus right in the middle, which is where the protons and neutrons are, and then outside of that you have these energy levels or rings where the electrons exist. So it looks like a bullseye. Okay, electrons are here, and that's really useful for showing these energy levels and where the electrons exist. More accurate is this idea of more three-dimensional of a cloud of electrons around an atom. Okay? So there's different models that are useful for different things. All right. Subatomic particles. Okay. You should know these, of course. You probably do, but you have protons, you have neutrons, and you have electrons. Those three basic ones. And actually, protons and neutrons exist in smaller particles, but we're not going to get into that. You can write little symbols of those. Okay, so proton, I'm going to put a P plus. Neutron, I'm just going to put a little N. Electrons, E minus. So if you see those, those are the symbols for those subatomic particles. Locations of each. Okay, you probably know. Neutrons are in the nucleus. Neutrons are in the nucleus, and electrons are orbiting around the outside. I put orbiting in that cloud around the outside. Okay, so they're on the outside there. Okay, mass. Okay, we say protons are 1 atomic mass unit. Okay, they're actually like 1.64 times 10 to the negative 24th grams. Really, really, really small. Okay. So we just say 1 atomic mass unit for both of those. So they both have, protons and neutrons have about the same mass. The electron is much smaller. It's 1 over 1840 atomic mass unit, which kind of makes it nice because they're so small that you don't even worry about the mass of the electron when you're figuring out the masses. And then charge, protons are plus charge, and neutrons, no charge, and electrons, negative. Okay, so I'll put a 0 here. Okay, so make sure you know those subatomic particle properties. Then into terms which you'll need to know. Atomic number is probably the most definitive thing about an atom or an element. It tells you which one it is. If it has a certain atomic number, it's going to be that atom. Okay? So it is just the number of protons. Simple. Okay? So if something is atomic 6, you just look on the table here. Atomic number 6 is carbon. Okay? Atomic number 8 is oxygen. Atomic number 92, the largest natural element, uranium, right? So atomic number, number of protons. Mass number is number of protons plus number of neutrons. Okay, so protons and neutrons. That makes sense because you look here, mass. These both have masses. You don't worry about the electrons because their mass is insignificant. All right. Isotopes. Elements exist in isotopes, which means they have. These isotopes are atoms which have the same atomic number. They have a different mass number. Okay? What that means, if you break it down further, they have the same number of protons. Okay? They have a different number of neutrons. All right? Okay, because isotopes make up the element. Okay, so if you have a particular element like carbon or chlorine, okay, they're going to have various isotopes which make them up, okay, in combination. 2 or more isotopes make up elements. Okay, so the atomic mass is defined as the average mass of all the isotopes of that element in nature. All right, so let's look at this real quick here. If you take, for example, let's take chlorine. Chlorine can exist like this, Cl 1735. When they show it like this, the bottom number is the atomic number and the top number is the mass number. Okay, so in this case, this chlorine, it's got protons, neutrons, and electrons. Okay, so this is the, just said this is the atomic number. Okay, and up here, I'll squeeze this in here, that's the mass number. All right, so you can do a little bit of math here, but for protons you don't have to. If it's 17, that's the number of protons. And if it's neutral, it's got the same number of electrons, so 17. And then neutrons, well, what's got to happen is the mass number has to equal protons plus neutrons. Protons plus neutrons. So if I go over here for this one, I know the mass number. Let's put it in here, 35 will equal 17 plus blank. Okay, so you can either figure that out or you can just go 35 minus 17, okay, and that would give you 18. Okay, so this particular isotope of chlorine has 17 protons, 18 neutrons, and 17 electrons. Okay, chlorine also exists like this, Cl 1737. Okay, so let's figure this one out. P N E minus. Okay, well that's going to be pretty easy. 17. Okay, and to get neutrons, mass number minus protons, 37 minus 17 would be 20. And then electrons, if it's neutral, can have protons and electrons got to balance each other out. Okay? So that's, if they are the same number, there's not going to be any charge on it. Okay? That brings us to the last concept here, ions. Ions are charged atoms. Okay, so you can have a plus charge or a minus charge. Okay, so let's look at chlorine real quick here. Chlorine, okay, generally gets a 1 minus charge on it. Now, if it's a 1 minus, sometimes they just go minus and it's assumed to be 1, or you can put a 1 minus there. Okay. Because generally what happens with chlorine is it has this number here, it usually tries to gain electrons, so now it becomes 18. So if you have 17 positive charges and 18 negative charges, okay, it's got 1 extra here. So, okay, it's got a 1 minus charge, that means it's got to have an extra electron. Okay? So A lot of chlorine atoms have this 17 protons, 18 electrons, and that would make it a negative ion like this. Okay. Something like sodium, Na, it's atomic number 11, so it's got 11 protons. Okay. It has, one of the isotopes has 11 neutrons also, and then it has 11 electrons. Okay. But a lot of times what will happen with sodium, it'll get rid of one so that it only has 10 electrons. And if that's the case, it's got 11 positives, only 10 negatives, so that's going to get it a 1 plus charge. So we call this a sodium ion. It is a called it's a positive ion or a cation. And chlorine is a negative ion or an anion. Right? So charged atoms that can be positive. I'm going to put cation is positive. Anion is negative.